It's the next functional group. So if we quickly go back and look at table R and we find the ketones, okay, there's lots of helps here for us. So if you notice, we are given a ketone name. So whenever we write a ketone name, here we have our example of what a ketone name should look like for us. We see what the functional group is. So we have to add a double bonded oxygen to the structure, okay? And when we take a look at it though, it has to be on an internal, not a terminal carbon, on an interior carbon. So let's look at a couple of examples here. So here we go. We're going to start off here with this structure. So we have a 3-carbon chain, and it requires 8 hydrogens to be attached to it. And because it's a 3-carbon parent chain, so here's our parent chain. So N equals 3. That means that we use the prefix prop, and those carbons are only linked together with single bonds, so this is propane. Now, if we put this through a substitution reaction, okay, so we're going to put this through a substitution reaction, we are going to add an oxygen to the structure. So the substitution reaction. This oxygen is going to come in and it's going to kick those hydrogens out because it wants to attach right there. So this is what we have when that substitution occurs. So we still have our 3 carbons in the parent chain. Carbon number 1 still has 3 hydrogens attached to it. Carbon 3 at the other end still has 3 hydrogens attached to it. Now, carbon 2, instead of having 2 hydrogens attached to it, now it has that double bonded oxygen. So if we take a look at it, okay, so we still have a 3-carbon parent chain. The carbons are still linked together with single bonds. So this would still be based off of propane. But because this double bonded oxygen is on an interior carbon, so this would be what's referred to as an interior carbon, then we understand that this is a ketone. So we have to drop the E and replace it with, it looks like 1, but we pronounce it own. Like a common ketone you guys would be familiar with would be acetone. So this would be known as propanone. Now, take a look. There are more carbons in this chain. What if I create an isomer? So an isomer, it has the same molecular, different structure. So I'm going to write myself a note. Same molecular formula, but a different structural formula. And all I'm going to do is move this double bonded oxygen one place to the right. So here we go. So carbon 1 still keeps its 3 hydrogens. Carbon 2, it had that double bonded oxygen, but I'm going to move that double bonded oxygen to carbon 3, right? But carbon 3 had 3 hydrogens. So carbon 3 with the double bonded oxygen, it now has 3 bonds, so it needs 1 more bond. So I'll add a hydrogen on there. But there's still 2 more hydrogens, right? And carbon 2 in the middle, it only has 2 bonds. So I'm going to add those 2 other hydrogens here. So when I take a look at this, now this guy, that double bonded oxygen, it's on a terminal carbon. So when I take that double bonded oxygen and I move it to a terminal carbon, it's no longer a ketone. This is an aldehyde. So this would not be propanone, this would be propanal. So they have the same moleculars, right? So their moleculars are C3, H, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Oh, 1, 2, 3, 1, 2, 3, 4, 5, 6, and 1. So they have the same molecular formula, but the structure is different. The double bonded O is on an interior carbon in the ketone, and the double bonded oxygen is on a terminal carbon in the aldehyde. So little things to watch out for. So let's skip down to this one right here, the bottom one. So we're going to start off with a 5 carbon, 1, 2, 3, 4, 5. And if we put all the hydrogens on, and I have to draw 12 hydrogens. So this is the simple hydrocarbon straight chain pentane because N equals 5. So this is pent, 5 carbons, and it's ane because they are single bonded to each other. Okay, so I'm going to make a ketone. So I'm gonna do a 5 carbons. I'm going to keep them linked together with single bonds 1, 2, 3, 4, 5. And I am going to put the double bonded oxygen here. Because I'm going to run out of room, I'm not going to put all of the H's on here with this. So instead of having 12, there will be 10 on here. I'm going to draw another structure. 1, 2, 3, 4, 5. This is on carbon 2. Now I'm going to move it one place to the right. So here we go. And then I'm going to draw another structure here. 1, 2, 3, 4, 5. And I'm going to move it, that double bonded oxygen, one more time to the right. I'm going to draw one more structure. 1, 2, 3, 4, 5. I'm going to move that double bonded oxygen one more to the right. So here we go. My first structure, 5 carbons, single bonded, so that's based off of pentane. But I have a double bonded oxygen on an interior carbon, not terminal. So terminal, terminal, interior. So this would be pentanone. Okay. I'm going to move to this next one. 5 carbon chain, single bonded, so it's based off of the pentane. I have a double bonded oxygen within the interior part of the chain, so it's a ketone. So I'm going to write it down as pentanone. Okay. Here we go. This one here, I have a 5 carbon chain, single bonds, so it's based off of the pentane, double bonded oxygen in a center or interior carbon. So this is a ketone, pentanone. And this last one, I have a 5 carbon chain. They are linked together with single bonds, so it's based off of the pentane, but I have a double bonded oxygen, but this is terminal. So here we go. This is no longer a ketone, but an aldehyde. So it's still built off of the pentane's backbone, but it doesn't end in -one because it's on a terminal carbon. The ending has to be Al, so pent and al. So now what we have to determine here, are these all the exact same structure or different structures? So here we go. We need to take a look here, and we need to number left to right. And when I look this way, the double bonded oxygen is on carbon 2. When I come back the other way and I renumber, 1, 2, 3, 4, 5, right back to the left, it's on 4. So I would choose the lower one. So this would be called 2-pentanone. I need to do the same thing on this pentanone. So I'm going to number my carbons left to right. And when I go left to right, that double bonded oxygen is on carbon 3. And when I go back the other way, renumber in the opposite direction, the double bonded oxygen location is also carbon 3. So that just means it's dead center. So the designation here is 3. So 3-pentanone. So we have 2-pentanone, 3-pentanone, we have pentanal. Now we got to take a look at this last example here. So looking at this one, left to right, carbon 1, 2, 3, 4, 5. The double bonded oxygen would be on carbon 4. When you renumber and look at it in the opposite direction and you do your numbering, the double bonded oxygen is on carbon 2. So we choose the lower number designation. So this would be 2-pentanone. So here we go. These two molecules are the exact same thing. They represent, it's just one molecules are in constant movement. So and one just flipped over. So these are the exact same molecule. So these 2-pentanones, they are the exact same molecule, just flipped over. However, the 2-pentanone, 3-pentanone, and pentanal, they are isomers. So these guys are isomers. And same thing here. These guys are also isomers. And these guys are isomers. So we have 3 isomers by drawing this out. So now let's just translate one of these names into a structure. So here we go. We have 2-hexanone. Always start first by finding your table P prefix. So hex is on table P, and hex means N equals 6. So I'm going to draw my 6 carbons. 1, 2, 3, 4, 5, 6. And then I notice, okay, it's an, which means ane, so it's an alkane, so it's all single bonds between those 6 carbons. And I notice that it ends in O-N-E, so that means that it's a ketone. So I have to add a double bonded oxygen to the structure. The 2 tells me its location. So I'm going to number just left to right. Carbon 1, 2, 3, 4, 5, 6. So when you're drawing, just draw left to right. So I have to put this double bonded oxygen on carbon 2. So I'm just going to place it there. And when I have everything that's in the name, now I go and add hydrogens to make sure each carbon has its 4 bonds. So carbon 1 only has 1 bond. so I need to add 3 hydrogens to it. Carbon 2 already has 4 bonds, no hydrogens. Carbon 3 has 2 bonds, so we have to place 2 hydrogens on it. Carbon 4 already has 2 bonds, so 2 hydrogens are added. Carbon 5 also already has 2 bonds, so we only add 2 hydrogens to it. And carbon 6 only has 1 bond, so we add 3 hydrogens to it. So a full-blown structure. So let's take a look at the condensed. So carbon 1, it has 3 hydrogens attached to it. Carbon 2, no hydrogens attached to it, just the oxygen. Carbon 3 has the 2 hydrogens attached to it. Carbon 4 has 2 hydrogens attached to it. Carbon 5 has 2 hydrogens attached to it. And our last carbon 6 has 3 hydrogens attached to it. So when we take a look at this condensed formula, here we see that sequence of COC that we look for to help us recognize a ketone.